This video will present you the new theoretical model for voltage plane analysis on remote field data. We decided to develop such model for helping user having some issues with the voltage plane as it was in the previous version. So first objective was to simplify calibration of a single driver and dual driver by making the support plate signal easier to measure. Second, make the tool very efficient if you're nulling or not the probe. Third, suggest optimum frequency on unknown calibration tube. 4. Suggest optimum compensation frequency for a heat exchanger having different properties of your compared to your cal tube. And 5, the most important, dynamically compensate the sizing for a tube having different material properties. The new RFT model is compatible with any setup that you have for remote field, created with the wizard or created with the advanced setting. To use it, we just have to go into the RFT tab and you select the second option here called calibration setting. From there you will see the list of available absolute channel on which you can apply the model. For this demo, I will just apply it on the frequency 1. Important, during the calibration, you will have to identify a nominal point for the calibration and also measure the support plate. On top of those two references, you need to add some defect, known defect, to be measured to set up the model. There is a suggestion here of defect that you could add. So here in my cal tube, I have two 360-degree large groove. So I'm going to use this to calibrate. So let's add a first defect. So the list of reference point is listed. So I'm going to select my groove 40. And it's the 360-degree defect. And then I will add my groove 60. And I'll also identify it as a 360-degree defect. The model could work if your defect is not 360 degree, like if it's a wear scar 180 degree. Just make sure that you don't check the 360 degree. And it could also be used on taper defect. In this case, it's only used to measure the amplitude of the signal, not necessarily the phase, because the depth is not constant over a taper defect. But let's assume that we start with groove, which is the best case scenario. So I'm going to click add, OK, and from there a new channel is created. So I would change my layout to show for the absolute model F1. So there's a small M just beside the name of the channel. I'm going to select this one for both strip chart, and I will set one voltage plane on the model and keep the second voltage plane on the same frequency but with the conventional absolute channel. So during the demonstration I will always compare both the model and the current or the previous voltage plane usage that we have in the other version. Let's start with an unknown calibration tube for which we're not sure of the optimal frequency. So in this case I recorded a data file of the cal tube with the frequency that was too low for the material properties. So normally to calibrate the remote field data, we first have to measure manually the support plate in the voltage plane and then do the usual calibration. So let's start by calibrating the old model and then we'll do it with the new model. So with the old system we had to select the support plate at the end here, and typically people were looking at the support plate signal, trying to locate the nominal point right here, access the manual measurement mode, and trace a vector from the nominal parallel to the main orientation of the support plate, and then doubling the signal to provide the expected 0 point at the end of the arrow here. So by doing this and normalizing, it was bringing the signal correctly in the voltage plane. I'm used to do that step and normally when I'm doing it, I'm quite right. But the only way to check if the signal was well calibrated was to look at the signal and see if the groove were reaching the 360-degree curve, which is quite good in this case. But sometimes it could take many trials before getting these results. Then a normal calibration will be done. With the new RFT model, you don't need to do this manual measurement anymore, and there's no fancy adjustment of a manual mode for the dual driver probe or the single driver probe. You just do a calibration as you do for the differential. So let's start the calibration, and we'll just measure all the flaws that we have. Remote field is best suited on the absolute channel if you use the average peak measurement mode. So I'm going to set the average peak measurement mode for all the absolute. Internally, when we do the calibration, it's this measurement mode that the system uses. So it's better to look at it this way. So let's start by measuring the first flaw, which is the first groove. Then we'll do all the flaws, 60%. The hole in this case is right here. Then I'm going to select the 20% signal. These are for the differential signal. I've got a flat bottom hole 60. Again for the differential, and specific to the new model, we need to measure the nominal point. So you place your cursor between two defects so that the signal will be in a good area. Select nominal and measure it. And for the support plate, there's we need to take care of doing it correctly, but the procedure is fairly simple. For a single driver probe, you just pick up the entire signal and the measurement will be right. For dual driver probe, what I suggest is zoom on the support plate to look at the general shape, and there's always a straight portion like this here that normally we use for the measurement, starting at the nominal, and then you see this straight portion. So to measure this, you place the first cursor in a good area, and then you adjust the second one to just pick up the first portion of the support plate signal like that. And what you look for is that this big dot line here, it should be in line with the straight portion of the support. It's not important the orientation of the vector, as long as this dot line is parallel to the straight portion of the support, the measurement is okay. So you make sure it's selected, you measure and calibrate. So once the calibration is done, you've got a message telling you if the frequency is good or not. In fact, if the frequency is good, there will be no message. But if the frequency is wrong, you will get a suggestion to change the frequency, in this case around 470 Hertz. I was previously at 300 Hertz, and the phase shift is not high enough to perform a good inspection. So if I click OK, I will see the results of this calibration, which will be good, but will provide less phase shift than what we normally do for remote field. So if I look at the signal, everything in the voltage plane is very well oriented. If I look at the differential response, I've got my hole set at 90 degree. But if I look at the phase shift of the 20%, it's only at 135 degree, which is not much. Normally we try to be between 150 and 160 degree when the hole is at 90 degree. So that's why the system has recommended to increase the frequency. What I can do to better see the phase shift between the flaw is to activate the phase to depth display for both the normal absolute channel and the absolute channel on the model. You can see that the lines are fairly similar, but they are opening more on the model for the deep defect, which is what we expect to do. Based on the recommendation, I scanned the tube at a frequency around 470. In fact, I selected 450, which is quite close, and I created that data file here. So now what we need to do is to recalibrate with the new frequency to make sure that the phase shift is correct. So I'm going to go quickly through the same process. But before that, I will renormalize the signal for the usual absolute model, because this is not set automatically during the calibration. So I take a good area and I renormalize here to make it right there. But for the model, I don't need to do that. I'm just recalibrating. Like we did previously, we just have to measure all the flaw carefully, and we take good care to correctly measure the support plate. And when it's completed, we can just hit calibrate button. This time I got no message. That means my frequency is suitable for the inspection. So if I adjust all that, I can see here my phase shift as open. So I've got more phase shift between each flaws, which will help to provide an accurate sizing. I have a similar phase shift for the old RFT model, a bit less open for the deep defect, but very similar. And on the differential, now I have my hole at 90 degree, and this time my 20% defect is at about 155. Usually you will know which frequency to use with your calibration tube because you use it on a regular basis. But that was an example to show you how this new theoretical model could help in case that you have a totally new material to inspect. Now let's simulate the impact of a material properties difference. So to simulate that, I changed slightly the frequency and rescanned the same tube. The reason for using the same tube is because I wanted to have known defect with known depth, so I can compare the sizing accuracy between the usual voltage plane and the new model. So before going there, I'm gonna save the current nominal position in the old model, so I can see now that my angle correction is at 0. On the new model, it's already saved and it's done automatically after a calibration. So now I read the first tube here. If I position the cursor in a good area, I can see that the nominal point has moved up, which means that this file creates less attenuation to the magnetic field compared to the calibration. So normally, such kind of variation in a heat exchanger tube, you will see that very often in your bundle. So the best or the optimal situation is to do a frequency compensation to bring the signal down to 0. But since you have that a lot of time in the heat exchanger, most people have come to just renormalize the signal when the change is not too high. So when we do that, it's bring back the signal correctly and you can size, but it also induces an error in the sizing. So depending on what you want to do and depending on how much the signal has rotate, there's various options here with the new model. First of all, you can decide to compensate for material differences. If you want to do that and want to have a suggestion for the right frequency to pick up, you can go into the RFT tab and click the check frequency button. When you do that, you need to make sure that the cursor is in a sound area, and when you click on it, the system will suggest you an optimum frequency for that material. And you see that the suggestion right now is 484 Hertz, and previously it was suggesting 470, so it's pretty close to the same recommendation. And again, it's an approximation. But instead of doing back and forth in changing frequency and trying to see which value I need to bring back the signal to 0, I can use that suggestion to do my compensation. Okay, let's say I don't do a compensation and I just want to normalize. So if I do it with the old RFT model, I make sure I'm in a sound area and I normalize. When I looked at the measurement I have after that, I can see that my 40% defect is now slightly underestimated. It's now 36%. And the reason for that is because the sizing curve are not updated to take into account that the material is less attenuating. And usually the error is more important when you go to a deeper defect. And here you see that instead of 60, I'm measuring 52%. It's not that bad, and it's a reason why we always say that remote field is approximately 10, plus or minus 10% when it's well used. But you can see that if the normalization would have been done on a bigger difference, my error could have been quite high. With the new theoretical model, the great thing is that we can dynamically change the sizing curve according to the normalization value that you do. So when I click normalize, you will see that the sizing curve are changing. They are getting compressed. And because they have this compression, I get more accuracy on the signal, or I maintain a better accuracy on the signal. So you see that the 40% is at 38.5 and my 60 is at 56.5. So not a huge value, but that kind of difference compared to the real value will be maintained even if the offset is higher than that. Now let's go back to the nominal of the initial cal tube, and I will read the second tube, which in this case is the opposite. The frequency has been increased to simulate the impact of a tube with higher permeability or higher thickness. So I can see that my nominal point has moved to the lower portion of the voltage plane, which corresponds to a more attenuating material. Again, I can just set my cursor in a sound area, normalize on the old voltage plane model. The sizing curve remains static, but now because the material is more attenuating, when I select the 40%, I oversize the defect because I have more phase shift than the original calibration. So instead of 40, now I'm overestimating this at about 46%, and my 60 is at 69%. If I do the same with the theoretical model, I just bring again in the nominal area and I normalize. And when I look at the signal, the accuracy is better. So the 40% is measured at 43.7%, but most importantly, the 60% remain very close at 61.8% compared to 69 here. It's a good improvement, and the accuracy is maintained between plus and minus 5%. So let's look at a variation in material properties that is even higher. So let's come back to the nominal value, and then I'm going to read this file where the frequency has been set even higher to simulate that impact. So you can see that the nominal point has even moved further down here. So there's almost 90 degrees of rotation that appear on the signal. So I can do the same and normalize in a sound area for the previous voltage plane. Sizing curve are not updated, and my 60% shows up at 73%. So it's a big oversized impact. If I do the same for the new model, and again I'm come here and I normalize, here I got a message or a warning, and it says that the variation I'm trying to compensate start to be quite high, and the system recommend me to, if I can, reacquire the tube to use a different frequency that I have right now. So instead of 600, it suggests to move it down to about 400. So it's not always possible to do that, But at least when you do analysis and there is a large variation, you are warned if it could be good to reacquire the tube eventually. That being said, the system will still try to compensate the sizing curve for that variation. So when I click OK, the sizing curve again are updated, and now if I move to the 60%, I'm still at 62.6% compared to 73%. So it's a very good improvement in accuracy. The system will tolerate quite well increase in material attenuation. When the signal moves down, we're going to maintain a good accuracy with quite large variation because the phase angle is increasing, so we can stay accurate. But on the opposite, if the signal is moving upward and have less attenuation, it will be more difficult to maintain the accuracy because by normalizing a less attenuating material, the phase shift will become very tight for different depth value, and it will be difficult to be accurate. This completes the demonstration of the new theoretical model. In the future, we're going to adapt this model to also compensate for differential signal so that not only the absolute and large volume defect will be compensated for material variation, but also the small pitting value will be adjusted in the same way. I hope this video will be useful for your integration of this new feature in your inspection. Thank you.